Welcome back to the Simkins Physics Corner. I'm your host, Mr. Simkins, and today, AP Physics 1 students, we are looking at the AP Free Response Question 2018 exam number 5. We've been learning about simple harmonic motion the last few days, so let's take a look at what a problem with simple harmonic motion might look like. Here we have a block of P of mass m, that's this one right here. Oops, okay. Block of mass m right there. Let me get my draw on here. There we go. Let's try that one more time. And nope, still no. Doesn't like me. How about now? How do you like me now? There it goes. I'll just keep it right there. The block P of mass m is attached to a spring with spring constant K. The block is oscillating with a period Tp and amplitude Ap about the spring equilibrium position x initial. A second block Q of mass 2m is then dropped from rest and lands on block P at the instant it passes through the equilibrium position as shown above. Block Q immediately sticks to the top of block P, and the two-block system oscillates with period T PQ and amplitude A PQ. The question here is asking us first to determine the numerical value of the ratio T PQ over TP. Now, there's a couple of terms in here we need to highlight. The equilibrium position. What else do we have? We have a sticky type collision, and that is about all we need to know. Now, since this is an oscillator, you see these little whoosh lines that they drew right there? That's what their technical term is for them, I believe. Those little whoosh lines are indicating that that block P of mass m is moving with a certain velocity as it flies through the middle. So the way this might have been set up is we might have had the spring stretched way out here, and this equilibrium position is where everything would be relaxed. So if I had a spring that could both squish and stretch, and it started here, and if I let it go, it would kind of just stay there. Maybe to get this thing going, I pulled the block from the equilibrium position over to here, said ready, set, go, and now it's oscillating back and forth. So at that point in the middle, that block P is moving with some velocity, so it has a certain amount of kinetic energy. And of course, over here, it would have started with some potential spring energy. So just a little bit of a background as to what's going on here. Now, if I pulled it back, you can imagine it would go boing, boing, boing. That's the technical term for it, back and forth. And T, the period, is referring to the time it takes, not just to get from here to here, or not even just to get from the right side to the left side, but T, the period of an oscillator, is defined as the time it takes to come all the way over and go all the way back. They call that completing one cycle or completing one oscillation, thus the term simple harmonic oscillator. And so let's go ahead and determine the numerical value of the ratio T PQ over TP. So really what we're asking here is, for a spring oscillator, how much is the period going to change as a result of adding this 2m into our system? At this point, you're either a genius and you've memorized all the physics equations, or you can go to the handy-dandy College Board equation sheet down there and look for the period of a spring equation. The period of a spring equation is given it to us here as 2 pi square root of m over k. All right. So the first question says, determine the numerical value of the ratio of the TPQ, meaning the period of the two blocks combined together, compared to the original period. So how much different is the period after we add this 2m? Well, let's consider this factor of change that we've heard so much about. Well, the factor of change is our system's mass was originally 1m, and then if this block of 2m sticks to the block of 1m, we now have a total mass in our system of 3m. So what does that mean? Well, that means that right here in this part of the equation, it changed by a factor of 3. It changed by a factor of 3. And so since the k stayed the same, this is a constant out here, everything stays constant. That's really hard to read. I'm sorry. I really apologize for that. How about now? It's still really hard to read. The mass is the thing that was tripled, and look where it is. The question says, what impact does tripling the mass have on the period? Well, the answer is it would have a factor of change. You can't just multiply this side by 3 for free. In fact, that's not what we're doing. We're multiplying this side by square root of 3. Right? You see the square root, and you see the 3 in the denominator. And so the answer for this one, determine the numerical value of the ratio of TPQ over TP, meaning the period of the 3m system as compared to the period of the M system, the answer is the period difference would be a factor of square root of 3. So that's a little ugly. All right, since it did say the ratio, you could do like square root of 3 to 1 or something like that. But that would be the answer for the first part, and that's simply coming from plugging in that change, that factor of change of going from 1m to 3m in the period equation. Now, physically, what does that mean? Well, just think about it. If I have a lightweight block of mass m bouncing back and forth, and then all of a sudden I make it heavier, isn't it going to take the spring a longer time to accelerate that heavier mass? And isn't that going to take a longer time period to oscillate or go back and forth? That is why this answer, square root of 3, what that implies is that it takes root 3 longer. All right, now that's a little bit, it's greater than 1, it's less than 2. All right, so let's just call it, I don't know, you probably know what the value is. All right, but it's going to take longer for that heavier block to go back and forth. And that makes a lot of sense if you think about that in the physical context. All right, I'm going to need to erase this because our next part of the question says the figure is reproduced above. How does the amplitude of oscillation of the two block system compare with the original amplitude of the block P alone? So now we're talking about not period, not how long it takes to go back and forth. We know it's going to go back and forth in a slower fashion if we add that mass on there. But now the question is amplitude. But what's amplitude? Amplitude is defined as how far the block is displaced from that equilibrium position in our system. So for example, if I had a spring and it started like this, if I just pulled a little bit and it went back and forth a little bit, that would be a small amplitude. If I pulled it like this, and then the oscillator went way back and forth, that's a bigger amplitude. Amplitude is the distance that the spring goes from the equilibrium position. So let's talk about the details that would happen. Now we have to read this very carefully and not get too hung up on simple harmonic motion because all of these physics concepts come together here. Notice that it says that when we drop this block on, the block sticks to the top of block P. Oh, they're running into each other, a collision, and that collision is sticky. So what kind of collision is that? I hope that the word inelastic collision is coming to mind, and an inelastic collision is one in which the energy is not conserved. Oh, that's going to be important. Why is that going to be important? Well, because the amplitude of a simple harmonic oscillator, how far it can go, has to be linked to its energy, of course. If this thing is zooming through here really fast, then the spring is going to go really far if it's zooming really fast. That has a lot of energy, right? If it doesn't have a lot of energy, it's not going to go very far. So the more energy we have, the bigger the amplitude, and the less energy we have, the smaller the amplitude. Okay, so how does this all come together? Well, it's saying how does the amplitude after the collision compare to the amplitude before the collision? And so after the collision, what's the difference? Now we have more mass, but how did that mass get there? Let's go ahead and start to unpack this answer and see if we can arrive at it as we describe it. I'm just going to type it because it makes things a little easier. All right, so the first thing we want to note is that the blocks collide inelastically. Okay, so we can say, all right, the blocks collide inelastically as identified in the sticky collision. And an inelastic collision is one in which the energy, actually let's be more specific, kinetic energy of a system is not conserved, right? By the very process of sticking together, there's going to be some energy loss, whether through deformation because they're sticking together, or maybe some friction, something in there. So the question says, in a clear, coherent paragraph length response, to indicate how does the amplitude change. So the blocks collide inelastically, as identified by sticky, and an inelastic collision is one in which the kinetic energy is not conserved. All right. Since the collision happens at the equilibrium position, where all the energy in the simple harmonic oscillator is kinetic. You guys follow that, right? As we go through the middle, there's no energy stored in the spring at the equilibrium position because the spring would be at its resting position at that time. So since the collision happens to be at the equilibrium position where all the energy in the simple harmonic oscillator is kinetic, the reduction in the kinetic energy of the system by the inelastic collision. I can really spell good, can't I, here today? Probably should learn how to touch type, get with the program here. The reduction in kinetic energy of the system by the inelastic collision means that the system now has a smaller amount of total energy. That amount of energy is going to also dictate how far away from the equilibrium position the mass can travel, aka amplitude. Okay, so here's our argument so far. Blocks stick together. Sticky is inelastic. Inelastic means you lose energy. If you lose energy at the middle there, that means we've reduced some of our total kinetic energy. If we have less total kinetic energy, then that means we don't have as much energy overall to carry us as far out. And so the answer here must be, all right, therefore, the APQ, that means the amplitude of both blocks together, must be less than the AP. Okay, and so for this one, you want to make sure you're checking the box too. Don't write an awesome paragraph and not put it over here, although they'd probably give it to you. APQ is less than AP. All right, so this is a paragraph length response. It's clear, it's coherent. It did say you can put diagrams or equations. You might want to you could add a few of those, but let's look at this holistic idea. All right, the blocks collide inelastically, as identified by the sticky collision, and an inelastic collision is one in which the kinetic energy is not conserved. Since the collision happens at the equilibrium position, when all the energy in the simple harmonic oscillator is kinetic, this is why I like typing these answers, and you should do so in your take-home response. Since the collision happens at the equilibrium position, the point at which, see, it just sounds a little better, sounds smarter. The point at which, if I can spell right, it sounds smarter. All the kinetic energy in the simple harmonic oscillator is kinetic. The reduction in the kinetic energy of the system by the inelastic collision means that the system now has a smaller amount of total energy. That amount of energy is going to also dictate how far away from the equilibrium position the mass can travel, aka amplitude. I'll add this because, and there's an equation on our equation sheet that helps us out with that. Well, we don't need the equation sheet. All right, we could say because at the farthest point from the equilibrium position, I'm going to abbreviate now, all the energy is stored as US. Since US, you're allowed to do this. They understand what you're talking about if they're physics people. Since US is determined by 1/2 kx squared, and x is the amplitude or distance from equilibrium position, this means that less US is available, so the block will not travel as far. Now, your answer doesn't have to look exactly like mine, but you see how at the end there I wanted to read over my answer, and I wanted to modify it so that I am sure that whoever's reading this knows that I know what I'm talking about. All right, I said the amplitude, right, and I did talk that, but that amount of energy is going to dictate how far from the equilibrium position the mass can travel, because the farthest position from the equilibrium position, all the energy is stored as US. Since US is determined by 1/2 kx squared, and x is the amplitude, or distance from the equilibrium position, this means that less US is available, so the block will not travel as far. Okay, so I really capped it off there talking about energy. So to recap this problem, at the beginning, we just used the period equation that's right off the equation sheet. That's worth 1 point, and this is actually worth 6 points, this paragraph length response, and that's why you want to make sure you go back and read it and make sure that your answer is really solid. Here we saw the idea of an inelastic collision and how that comes into play. We saw the conservation of energy, and that helped us with our explanation. And we also saw simple harmonic motion. Most likely, these free response questions are not going to just be, hey, here's a simple harmonic motion problem. It's going to be a problem where you have to understand multiple units, especially since we only have 2 this year. So I hope you guys enjoyed this video. Be sure to like and subscribe in the Simkins Physics Corner. Hit the bell, ding, for the notifications. Until next time, this is the Simkins Physics Corner.